Good morning, ladies and gentlemen, and as my college thermodynamics professor would say, welcome to another wonderful day of thermodynamics. Everything is thermodynamics, and especially is the webinar on AFT xStream that we'll be discussing today. And yes, that's actually how you say it. I just want to thank all of you for joining me in the webinar today, and I hope that you are all doing very well and having a wonderful week wherever you are in the world. And so today we are going to discuss some new features that came out with our latest version of AFT xStream. We just released version 2 this week, actually. And so there are some powerful new features that came out with the latest version. We're going to go over a few of them and kind of just give a taste of what AFT xStream looks like anyway. And so here's our good old AFT software product overview page. We've got AFT Fathom, AFT Arrow, AFT Impulse, and AFT xStream. And what does xStream do? AFT xStream models gas hammer and steam hammer types of transients in gas piping systems. And so it's very similar to AFT Impulse, but it's for gas piping systems. So a very powerful tool and gives excellent results, and we're very excited about it. Now, a disclaimer when we talk about doing steam hammer is that it's not condensate steam that we're capturing. It's staying fully vaporized during a transient. And so don't get caught up in the whole debacle. Just it's modeling any gas phase piping system, whether that is steam or methane, whatever it is. And so one thing I want to point out is that AFT xStream does have a pulsation frequency analysis add-on module. And what that will do is it will ring your system to determine what the acoustic natural frequencies are. That way you can check the various codes to make sure that you're within compliance and not exciting frequencies that can cause resonance in your system that will tear itself up over time. So that is something that is available as well. All right, something that is really useful about our latest versions of our software is that the help file is on our website. So if you go to aft.com, you can access the help site even without having a license to the software. And so once this page loads here, then we'll be able to take a look at the help file for AFT xStream. I seem to be having a little bit of a internet delay, and now it's starting to come up, it looks like. And okay, well, also the good old-fashioned way to get to the help file is to browse to the help menu within the software itself, and then just click Open Help. And that will also bring you to the AFT help file, which for some reason my internet is just having trouble, so I'm not sure why. Sometimes you just got to try refreshing the page. Well, anyway, it's there. You can go there right now if you want to check. It is there. It's just taking my internet longer today than it should. So anyway, we'll go ahead and get started and talk about some of the new features that came out with our latest version here. And so I wanted to start off with some more simple, basic ones. With AFT xStream doing transient modeling, you can model finite tanks, and this is really useful for doing tank blowdown types of calculations. And so that's what we're going to be demonstrating today in one of the examples that I have for you. And so if you choose the finite option, you can specify your initial conditions for pressure and temperature, or you can calculate what they are from steady state conditions. And then in the previous version, the only options for thermodynamics that you had was to assume either a adiabatic tank or an isothermal tank. Those are the only options. Now you're able to model a known heat and volume versus time. So if you have a heat rate that you know, as well as knowing how the volume might change, then you're able to model that as a changing heat rate and volume versus time transient profile. Now that's for a flexible type of tank that is not rigid. If you are using either of the other options, adiabatic or isothermal, then whatever volume you specify right here, that's going to be a fixed volume to assume that we're modeling a rigid tank where the volume is not going to change over time. Now you will see how the pressure and temperature and mass inside the tank changes during the transient simulation. And so that is certainly something that you would want to evaluate. All right. Next up for some of the, one of the new features is our, with relation to our thermodynamic properties. And so you'd be familiar with this if you've used AFT arrow in the past, where we have good old Redlich-Kwong as the default ideal gas constant Z, but there are some new ones in here. We also now have the Peng-Robinson and Soave-Redlich-Kwong equations of state. So some more accurate equations of state are available for you to be able to use and work with. And you can do comparisons to see which equation of state gives you the best results and the most accuracy. So that's where you can turn on not turn on, but where you can use the various equation of state models. So that is something that we're excited about, is just being able to expand our thermodynamic property data sets. Another thing that is helpful is that with AFT xStream, the AFT standard database of fluids now knows where the saturation lines are. So if you get to a temperature during your simulation that is below the saturation temperature, then you're going to get warning messages telling you that that's happening, and that would mean that condensation is present in your system. And if the model is even able to converge, you'll definitely have some big warnings, and the results will be uncertain at that point. Your next charge would be to try and determine how do you eliminate the condensation that's happening. And once you eliminate the condensation, then the results will be able to be a lot more trustworthy in that regard. And so, okay, our web page finally loaded with the help site. And so here's where you can find all of our help files for AFT Fathom, Impulse, Arrow, and xStream. And again, you don't have to have a license to be able to actually access the help site. And so if you click on AFT xStream, then you will be opening the help file, obviously. And I want to show you where you can find some more information about all of our new features that came out with version 2. If you expand the overview of AFT xStream, here's where you can find the topic for the new features in version 2. And you can read through these, and it gives you some screenshots and some brief descriptions to see what was added in, as well as some links to where you can find more information about that particular feature. This is another one that we're really excited about, is much better reorganization of warning messages. And so, as you can see here, we have color-coded them by caution messages and warnings or critical warning messages, and we've grouped them accordingly. This just makes it much easier to be able to diagnose the various messages that you're seeing in the output, and when they're all previously the same text color, it was kind of a little bit more tricky to determine which ones were, really threatening, if you will, and which ones are, things that you might be able to deal with and are just more informational types of messages themselves. And so this is what you'll see is a much better reorganization of messages. Also, in that regard, let's say that you had several scenarios that you wanted to run sequentially and get results for. Once you're done doing your run, it'll actually tell you in the window that has information about all the scenarios that finished, which particular scenarios had warning messages and which scenarios had design alerts that were present. And so if you specify a design alert for a maximum or a minimum pressure or temperature that can't be exceeded somewhere, then you'll see those on the design alerts tab as well. And so this will help you better analyze your data. And just as the tip says here, for an explanation of warnings, click on any of these items. It'll take you to the help file where you can get a more thorough discussion on what each of the different warning messages means. If you wanted to take a look at some tutorial examples for how you would use AFT xStream, you could scroll down to the bottom in the examples section, and this is where you can find our summary, and there are several different types of examples. One of the main ones I'm going to demonstrate today is this tank blowdown, and then if there's time, I'm going to show another example that I brought in actually from AFT Arrow and slightly modified it. So that's where you can find the help file and all the content with relation to AFT xStream. A tip is to spend time when you are learning xStream, really make sure you go through all of these examples. Unless if you don't have the PFA module or if you don't need it, you don't need to worry about that one. But the rest of them are critical to work through. This is one of the key differences between AFT xStream in comparison to our other software that you might be familiar with. xStream is much, much more like a true computational fluid dynamics CFD type tool where with the nature of compressible flow and how you will need more sections in your analysis to be able to get more accuracy, you're going to be facing some longer run times. Now the question is, when can you get away with a more robust model versus really tightening things down with more sections and still maintain an accurate model and not have a super long runtime? And that's that's the $1 million question. That's something that you're just going to have to study right there. And so that's where sensitivity analysis is really helpful. You can follow through this example and this one, and those two examples will look at different thermal property packages and different amounts of sectioning, and you'll be able to kind of get a picture for how much that actually impacts your results. All right, there are a couple of new junctions in AFT xStream that were not in the previous version. You're able to now model elbow junctions as well as venturis and screens. There's not too much more excitement other than they are there and you can work with them. A venturi is simply a device with a loss model, either based upon a K factor or a discharge coefficient or a resistance curve. And so just gives you a little bit more flexibility than what you have before. But ultimately, if you specify a venturi with a resistance curve and you use the same exact data for a valve with the, well, I guess a valve you can't do a resistance curve. If you did a general component with the same resistance curve, you're going to get exactly the same results, just two different ways to do the same thing. All right, a couple of other things here is when you're trying to toggle junctions on and off to close them, for example, like in this blowdown model, this valve here is initially closed. And so that's called a special condition. And so if you go to the optional tab, this is where you can find the special conditions. And so for a valve, there's only one. It's either none, which means that the valve is open and it's at whatever position it's in, or it is closed. And so there's only one special condition that you are dealing with. So if you were to select that junction on the workspace and then you were to click this red circle with a slash through it, that will toggle the special condition on and off. Now, let me open up that blank one again here. Let's say that I have a tank and another tank and a control valve instead. So if I have a situation like this, control valves will force a specific pressure set point or a flow set point or a constant pressure drop. And if you go to the optional tab, there are two special conditions. You can either fail your control valve closed or you can fail it open, where it's like it's not even controlling at all. It's just stuck open and it's not trying to achieve your set point. So here, when you have multiple special conditions, the enhancement is that this icon on the toolbar allows you to choose between which one you want to work with. Either closed, you can see how that closes off the flow path. That's why these lines are dotted. And then you can also set it to fully open, no control. So the little red X, that means that you have a special condition defined for that object, but here in this case, it's got flow through it, so the pipes are solid. And that is really helpful because you might have several control valves or maybe several compressors that have multiple special conditions like that you want to toggle on and off, and you can select all of them and simply go to the toolbar and toggle it however you like. So that is our special condition enhancement. And one of the last things I wanted to talk about here with the basic enhancements for the latest version is our new library manager. And so this is something that is also available in Fathom and Arrow and Impulse in the latest versions. And if you go to the library menu, this basically replaced what we used to call databases. And in here is our library manager. We basically made it easier and more consolidated to be able to access all of the different library pieces. For example, custom junctions, custom fluids, custom pipe materials, etc., all within a single window. Before, they were all in separate windows that you would have to go and access, so they've been consolidated and streamlined so that it's a little bit easier to work with. And so if you ever wanted to create a custom pipe material, you would just click on Edit Pipe Materials, and then if you wanted to create a brand new one from scratch, you would choose New Material, and then you'd be able to define the various pieces of information that you need here. Or it's actually a lot easier, when you're building your own custom pipe material library, it's a lot easier to do that in Excel. And so that's what the import from file button is for. So if you import from file, this tells you how you need to set up your spreadsheets. So that way in Excel, you can easily copy and paste rows of data and manipulate things much easier, and then just import that right in, and that will quickly build your custom pipe material library for you. So play around with that, and it's also really helpful for being able to create external database files that you can share with other people and make available. So be sure to check out our new library manager and the capabilities thereof. All right, now let me go ahead and jump into an actual example, and I'm going to talk about, for the majority of today, probably the most important new feature with AFT xStream that came out, I would say, is heat transfer modeling in pipes. And so in the previous version, the only option that you had available was adiabatic. That was the only option that you can work with. And if you're familiar with AFT arrow, your heat transfer characteristics very well can make an impact on your results for your, obviously, pressures and temperatures, but also your resulting flow rates and velocities that you'll see. And so heat transfer definitely plays an impact on your gas dynamics. And now you can actually get a feel for how much that is going to impact things. So if you were to build this model from scratch, that again is the tank blowdown example. I started with it and I took it just a little bit further. So let's go ahead and load in the base scenario just so that you can see what we're looking at here. So in the base scenario, then this is where we're starting off. And the analysis setup menu is where you configure what particular gas that you're dealing with. So this is modeling nitrogen. It's just a simple nitrogen blowdown simulation. This is where you define your pipe sectioning, and pipe sectioning is a bit complicated, so make sure that you spend time learning about how to do it properly. That way you can get the right results. And we are doing a transient simulation of 240 seconds because we don't know how long it's going to take for that tank to blow down. So this is why we're specifying a longer simulation period here. All right, so that's our setup there. And in the tank, I'm starting off with nitrogen at 600 psi and a temperature of 300 degrees Fahrenheit. And the volume of the tank is fixed at 300 cubic feet. And it's a adiabatic tank, so it's perfectly insulated. Next, we have a 2-inch diameter pipe, which is 20 feet long. And as you can see in the base scenario, it's adiabatic. We're not doing any heat losses through the pipes. Now, you would still see how the temperature changes in the pipe because of the expansion of the gas as it's flowing down the line, but there'd be no heat losses to the ambient conditions. And so now you can account for that, and we're going to see here that in a minute. Next, we have a valve where the valve is initially closed, and then we're going to open it very quickly within 0.1 seconds. So it's going from a fully closed valve to a fully open valve very fast. Gas will start flowing through it. And then next we have downstream is a 2-inch diameter, 1,500 foot long pipe. And we are simply discharging into the atmosphere. So atmospheric conditions is what we are flowing into. So out the end of a pipe. All right. Now, as I mentioned, AFT xStream, you're going to be dealing with some slightly longer run times. And so thankfully, I already have results for all of these scenarios. So I'm going to show you what's different in each scenario, and then we'll take a look at some results. So if you were going to run these before and you wanted to do a batch run, the way that you would do that is by going to the File menu. And then once you go to the File menu, you would click on Start Batch Run. And then you would add which specific scenarios you want to run. And then simply click on the Start Run button. So that's basically all that there is to it. I've already done that. So let me load up the next scenario here, where we are doing a free convection heat transfer thermal model. So we're going to see that the window looks a little bit different. When you specify heat transfer in a pipe, you'll see a little red square that indicates that you are modeling heat transfer in that pipe. So when I go to the heat transfer tab, I'm doing a convective heat transfer thermal model. You can also do convective heat transfer and heat flux. Maybe you want to account for radiation, solar radiation, solar loads, or do heat transferring. Those are available to you. One moment. Okay, and so here I have my resistance geometries through the pipe. Sorry about that, had a sneeze. I was waiting for that one. Okay, so we have the internal fluid heat transfer correlation using the Nolinsky equation. You can also choose Dittus-Boelter if you want. Nolinsky, I think, is available, or I think it's a little bit more accurate and for a little bit wider range of Reynolds numbers and Prandtl numbers, I believe. And then you're going to have your conduction through the pipe wall. And so this pipe here is, or we're using steel pipe with standard schedules, and our pipe material libraries knows what the densities are and the wall thicknesses. So that's how we're able to, or as well as the thermal conductivity. So that's how we're able to get conduction to the pipe wall. And then finally, for the external heat transfer coefficient, we're modeling free convection. So this is just free horizontal convection, where our ambient conditions are 70 degrees Fahrenheit. And if you wanted to do layers of insulation, you can add that right here. Either external insulation, internal insulation, or a combination of both. So that's the second scenario. Third scenario, I am doing a forced convection thermal model. So the only thing that I changed here was I set the external heat transfer coefficient to the forced convection thermal model, and then I specified a wind speed of 15 miles an hour. So that's not bad. This is a very nice day with a nice slight cool breeze. So that's my ideal conditions. Too bad we're getting pretty hot there in the summertime now. And then last but not least, for my very windy day, I specified a high wind of 40 miles per hour, just to see what our differences in results would be. All right, so now what we're going to do is we're going to start looking at graphs, and the graphing capabilities are just incredible. You can start off by creating graphs right from the workspace. So let's say you wanted to see what the tank conditions look like to start with. So I can right click on the tank, and there's two ways that you can create a graph. You can either create a transient graph for the junction itself. So these will be junction type results here. So this would be the pressure in the tank, temperature in the tank, the mass in the tank, etc. Or you can create a graph for the connected pipes. And there's several different parameters available here. Well, let's go ahead and start off with looking at the, well, let me switch to the base scenario. I'll look at it in the base scenario, and then we'll compare it with all the others. So I'm going to right-click on the tank junction, and I'll go down to generate a transient graph for junctions, and we'll look at the pressure. So, based upon a adiabatic tank and adiabatic pipes, we can see here that it's going to take about 240 seconds for the tank to go from 600 psia down to around 90 psia, somewhere around there. So in order to extrapolate this out to 0, maybe it takes 400, 500 seconds to completely empty the tank. You could run it longer if you wanted to. We just ran it for the 240 seconds. Now, how does this compare with the pressure in the tank for the other scenarios? This is another new feature that came out with Fathom 12 and Arrow 9, and it was also implemented in Impulse 8 and then enhanced further in Impulse 9. So it was already in xStream, but it's definitely a very powerful feature that is really worth mentioning. It is our multi-scenario graphing capability. So here, we're only looking at the results for one scenario. If you want to compare the other scenarios, you can click on that drop down and then choose Select Scenarios. So now I'm going to look at, let's just keep things simple and let's go scenario by scenario. So if I look at the forced convective heat or the free convective heat transfer scenario, and then I regenerate the plot, you can see that there's some slight differences here. And what you're seeing is if you have convection going on, this pressure tends to drop a little bit faster than if you were assuming an adiabatic process. So the results are still similar, but right here at a certain time, 72.6 seconds, we're already down to 283 psia versus 300 psia. So it's dropping a little bit faster that we can see here. Now, how does this change when we add on another scenario? Well, let's take a look at it. Let's add the forced convection heat transfer scenario and regenerate it. Okay, so in this case, this is interesting because the free convection and forced convection thermal models are actually providing very similar results. One of the cool things about the graphing capabilities here is you can use these checkboxes to toggle various data sets on and off. Excel can't even do it that easily. So if I zoom in here, you can see how the free convection and forced convection thermal models are very, very close to each other. There's not a lot of difference there. So the presence of wind versus if you had no wind and it's just sitting there, basically no difference in results. Now let's add the fourth scenario where we're looking at a very windy day. So if we're looking at a very windy day, then you can see here that a very windy day is still fairly close to the other two thermal models. So if we zoom in, you can see how the very windy day, the pressure is dropping faster, but still not as much. And so this is the convection comparisons with the adiabatic scenario. Now that's looking at pressure. How about the flow rate from the, how about the mass inside the tank? Well, let's look at it. So this is where we can get really fancy. You can add on a second parameter and third and fourth parameters, and I can choose mass in the tank, and let's just go ahead and keep it all 4 scenarios, and we'll generate it. And keep in mind that you're going to have tens of thousands of data points when you're doing these graphs. So it will take a little bit longer for these graphs to generate. So just be patient with it, give it its time that it needs to do what it needs to do, and it'll work well for you. So I'm going to modify the scaling a little bit here. You can just right click on the axis, and then we'll change this to 240 seconds. With every 10 seconds, make it a little bit easier to work with here. And so when we look at the mass inside the tank, you can also see that it's emptying faster by comparing it to the convective models. So when you have convection going on, you're going to have higher flows in the system, and that tank is going to empty a little bit faster than you think. Maybe that's a good thing, maybe it's not, but now the key thing is you can know exactly what it's going to do in comparison to the robust adiabatic assumptions that we're used to dealing with, which makes things a little bit easier, which is nice until it's not what we need to work with anymore. Okay, let's take a look at temperature. Now we can add on as many of these parameters as you want, but just to keep things a little bit simplified, let's just take a look at the temperature by itself. So we'll look at the temperature for the tank, and you can see how the temperatures change accordingly as well. If I go to 240 seconds, every 10 seconds. There we go. So temperatures are also dropping faster with convection, which is exactly what you would expect. But then they will eventually cross the adiabatic assumption, which is kind of interesting. You can see here where the adiabatic temperature, that starts to drop to become lower than the temperatures of convection. So this just gives more resolution as to what's going on. And then by the time that you get to the 240 seconds, we're back down where the adiabatic assumption temperature is the lowest and the convective temperatures are a little bit higher. All right, so that's where you might start when you first start analyzing this particular type of problem where you're doing a blowdown. That would be a good place to start. What's happening in the tank? After you take a good look at what's happening in the tank, then you might want to start taking a look at other things like the valve. But is there anything else we want to look at? No. And so now let's go ahead and take a look at the profile plot, where we're going to plot a flow path and we're going to animate our results. So let's start with looking at all 4 scenarios, and we're going to look at pressure. Move that out of the way, add on my labels, and I'm going to set this out to 1600. This is just really easy to modify your axes by right-clicking on them. Here I can make this go every 50 psi if you wanted to. All right, so this is our tank right here, J1. Then we have our valve, and then we have the atmosphere right over here. So what we're plotting is the entire flow path, and we're going to animate the results when we press the play button. So if I just click on play, things happen really quickly. So the time scaler for the animation speed is something that you're going to be working with quite often, where you'll be starting off by maybe slowing this way down, or even just going one time step at a time. So if you click on these buttons, you can go forward one time step at a time. That way you can control how fast the animation is going, so you can see what's happening a little bit more clearly. So we initially have a system that has no flow in it. The valve is closed and everything is just sitting there. Now, this presents a very important assumption that we are assuming, and similar to Fathom and Impulse, where those are modeling systems that are completely liquid full. Well, AFT Aero and AFT Extreme model systems that are completely gas full. Well, with the same kind of gas, so what that means is I'm modeling nitrogen in my system properties window here. So this entire system is nitrogen. What that means is if this is open to atmospheric pressure, in reality, we're going to be having air in this pipe. That's not being dealt with currently in any of our software, really. Right now, I mean, there's ways that you can kind of get around that and do a snapshot in time with Fathom and Impulse, but right here, in reality, you have air in this pipe, but AFT Extreme is assuming that that's all filled with nitrogen already. So in reality, you're going to have a situation where you have air in your system, and as this valve opens, the nitrogen is going to have to start pushing the air out of the system before you start to see nitrogen exiting. That's what the model is going to show. It's going to show densities in this pipe based upon nitrogen, where in reality, they're going to be air densities initially until the air is evacuated. So that's a very important assumption I just wanted to make clear that we're dealing with right here is basically where it's not, or it's similar to where Fathom does not yet model filling of evacuated piping systems. So same thing here. You wouldn't have an evacuated system, it would have air in it, but we don't have a mechanism yet that demonstrates that fluid interface boundary traveling down the line yet. So be aware of that when you get into your analysis. Okay, so here I'll start going one time step at a time. The valve starts to open, and now we start to get some pressure transferring through the line. And as you can see here, the adiabatic scenario is going faster than the convective scenarios. And we're showing slightly higher pressures in an adiabatic sense earlier on. Why is that important? Well, maybe your system is pressure sensitive, and so maybe how fast that pressure is increasing on an adiabatic basis is too high, too fast. And so now our pressure wave starts traveling down the system, and we'll go ahead and just play the animation. If I pause it and turn off very windy or forced convection, you can see how those are basically given very similar results to free convection. So not very significant differences there. So we have our pressure change throughout the system. If I go to default speed, it'll go a little bit faster for us. And basically from here, this is where we can simply watch the system pressure equalize. Now, this is still taking into account sonic choking. And so if you happen to have sonic choking, it'll tell you in your event messages. And so as we can see here, it tells me that my valve became sonically choked very early on, and then it lost sonic choking, meaning that it went subsonic fairly quickly later. And then we have sonic choking happen at the exit of the system. And so it's important to know where you are sonically choked at and when you start sonically choking, and xStream will be able to track all that for you. So this is basically how the pressure changes. So as you start to get later on into the animation here, that starts to equalize, and now our pressure decreases, and we have a non-linear pressure decrease where it's sonically choked at the outlet as it's discharging into the atmosphere. And it just keeps dropping and dropping, and that's what our system pressure is going to look like. And you can see how there is some differences in pressure due to convective heat transfer. All right, now let's take a look at the temperature in the system and compare the temperature in the system between the 4 different scenarios. All right, and we'll go ahead and make this be every 200 degrees. Okay, so initially we have constant temperatures in our system before we open up that valve. And so now let me go back to really slow speeds, and we can see how the temperature changes. So we have a sudden upset in temperature where the adiabatic scenario, watch this. The temperature in the adiabatic scenario is going to send a very hot thermal wave through the system. And so if you were not accounting for heat transfer with convection, then you might be thinking that you're going to have a lot of insulation to be able to handle those higher temperatures. And thankfully, that's not the case. So watch how, let me set it to default speed. See how high that thermal wave gets? This is the nature of fast transients with compressible flow, is when you first start to introduce flow into a system, you're going to have a sudden thermal wave that's going to pass down the system. So maybe your system is not adiabatic, but maybe your pipes are well insulated. Well, your temperatures are still going to change accordingly because there's no way for that heat to be lost through the pipe walls. So this gas can get to be very, very hot inside the pipes. And so maybe that goes to show where you need to slow it down when you're opening up valves and do things more slowly so that you don't have this sudden thermal shock that's traveling down the system. When you compare this to the convective heat transfer scenarios, these are much more reasonable. And so here you can see here that the temperature is right around 90 degrees and 80 degrees and dropping as we approach the outlet of the system, versus look how high that temperature gets, 1200 degrees Fahrenheit, and it's continuing to grow as it travels down the system. Is your piping system able to handle this really high temperature profile? That might be a problem in your particular system. And so this is why I say that the incorporation of heat transfer into the second version is probably one of the biggest improvements and most important new features with xStream version 2. Now, if we just continue forward here in the analysis with the animation, the temperature eventually kind of settles out. So after that really high thermal shock, you can see how the temperature does come back down. So within about 15 seconds, your temperature does get back lower for the adiabatic scenario, but it's still showing that your temperatures are almost 300 degrees Fahrenheit, where when you have convection going on, they're actually closer to the ambient temperatures, which is what we would expect. So that is temperature in the system. And let's see. Looking to see if we have heat rate, and it's not on here. So all these are different parameters that you can look at, you know, volumetric flow rate, dynamic viscosity. I was looking to see if heat rate was one of the parameters that you can graph, and looks like not at this time. But that's probably the next thing that you would look at. So in this analysis, we started off with looking at the supply tank, and then we started looking at the flow path, comparing all four scenarios to each other. And the way that you compare the scenarios is by clicking on this drop down, and then you can select your scenarios right here. And you can also eliminate ones in the graph so you can focus on one at a time, or just compare two of them that you might want to focus on. And so that way you're not having to be distracted with several other lines. It makes it really easy to be able to break things down and move it along bit by bit. After that, you can also add additional parameters to stack them on top of each other. So maybe I want to look at both temperature and mass flow rate, and maybe move mass flow rate to the top. This will create a stacked graph. You can also maybe do a third graph where you're looking at pressure in PSI A and then maybe PSI G. So if I move this over for the second row right here, I indented it, as you can see. That's going to create a secondary y-axis for this pressure, and we're going to set that to PSI G units. And if you're doing a secondary axis like this, it is helpful and probably important to set that to the same scaling as the primary y-axis. Makes it a little bit easier to interpret because it is auto scaling it for you, which I guess for animations it forces it to be the same. But if it was a static graph where you're not doing an animation, you'd be able to set that to be the same as the other. So 1600, then 100. And so now we can watch all three of these graphs at the same time. Mass flow rate, temperature, and pressure. You can change the title of the axes. So I can call this M dot if I want, and then just call this T and call this P for pressure. And now that I've formatted things how I like, you can then click on this folder with the blue plus sign on it, and you can file this away in our graph list manager. I'm going to call this Ben's animation. So now it is filed away in the graph list manager. A really useful way of filing away and organizing the different types of graphs that you want to work with. And this just gives you very rich data to be able to analyze really easily when you're looking at various parameters together at the same time. It makes it much easier to be able to understand what's going on in your system. All right. Well, that is basically what I had for you today with the various new features, and it was, it may not be as many as we usually will put out into a new version, but I want to emphasize that AFT xStream was just launched as a brand new product last year in 2021. So we already have a brand new version out available already, where now you can do heat transfer. And so there may not be as many features as we usually have, like in our other software that have been around for almost 30 years. But this is a brand new one, and we're already at version 2 with some outstanding enhancements. So keep posted for further enhancements down the road of things like moving choke points in a system and different things like that. So if any of you want to try out AFT xStream and take it for a test drive yourself, feel free to contact AFT directly if you're in the United States, or if you're in international areas, then please contact your local channel partner and they'll be happy to provide you some more information. Thank you very much, everyone, and have a wonderful rest of your week.